Okay, welcome to example number 10. This is called the Torricelli's theorem. We have an example of a large tank filled with water. It has a depth of 15 meters from here all the way down to the bottom. There's a spout located 10 meters from the base of the ground. And what we're looking for is what is the speed that the water would eject through this spout. So as with Bernoulli's equations, we always start to identify two locations where we can apply Bernoulli's equation. So we have at the top of the surface, we'll label that number 1. And then we have over here number 2 is where the water is exiting out the spout. So now we can write down the Bernoulli's equation and start to identify the different terms here. So we have pressure 1 plus rho g y1 plus 1/2 rho v1 squared equals pressure 2 plus rho g y2 plus 1/2 rho v2 squared. Now, if we look at this, we need to identify what all these different terms mean. We have pressure 1. Now, pressure 1 is basically, this is an open large tank, and we have air exposed at 1, and we also have air exposed at 2. So pressure 1 and pressure 2 are basically both the atmospheric pressure. Okay, so you can see that these two terms are the same, and really they'll cancel out. Then let's take a look at this rho g y1 and rho g y2 term. Now y2 would be this height. Now I could make y1 15 meters and then y2 10 meters, but that would give me two terms, and I think it would be easier to make y1 really just the difference between 1 and 2 here, which is just basically 5 meters above that, and y2 will make 0. And that means that term will go to 0. Okay, the density of this fluid, this is water, and water has a density of 1,000 kilograms per meter cubed. And the other thing we have to deal with now is the velocity. The velocity you have to look at here. The top of this tank is really large in area compared to this little spout area. So area 1 times velocity 1 equals area 2 times velocity 2, where area 1 is much, much larger than area 2, which means that velocity 1 will be much, much smaller than velocity 2. So we can assume that if this is really large area, that velocity 1 will be approximately 0 when you compare it to velocity 2. So that means that this term will drop out. So now let's see what happens to our Bernoulli's equation. We have pressure 1 and pressure 2 canceling out because the differential pressure is 0. We have y1 being set to 0, so this term disappears. And then we have velocity 1 basically approximately equal to 0. So essentially what we end up with is that the rho g y1 term equals 1/2 rho v2 squared. Or basically you'll end up with a velocity 2 will be equal to the square root of 2g times y1, because the densities have canceled out. And so if you look at this maybe if you recall back when we did kinematics, this is kind of like 1/2 mv squared equals mgh, and we ended up the masses canceled out, and we got velocity equals 2 square root of 2gh. Basically the same thing, because really it's really the same concept. I look at this term as like the amount of potential energy per volume, and this is like the amount of kinetic energy per volume. So now we can go ahead and substitute our numbers in, and velocity 2 is 2 times 9.8 meters per second squared times a difference between y1 and y2 was only 5 meters. So that was the 5 meters that was contributing to that extra velocity, and that gets you a velocity of 9.9 meters per second. Okay, so now let's go on to part 2, which is finding, or part B, to find the horizontal distance that this water travels. And this is a nice way of putting a fluids problem and mixing it in with kinematics. because you have this water that's leaving now, and you know that velocity. That was 9.9 meters per second, and hopefully you realize that's horizontal velocity actually when it comes out. And then this follows a trajectory that's like a parabola. That is actually a parabola. And what we're looking for is what is the horizontal distance, x, that it travels. Now, what you do need to use is the vertical height that the water drops. That's 10 meters. So we can write that as delta y. And we need to find the horizontal speed. And if you recall, how did we deal with things with projectile motion? Well, we need to find the time in the air. And so we go back to our kinematics equation, y equals y0 plus v0 yt minus 1/2 gt squared. The initial vertical velocity was 0. The final height was 0. We basically got delta y equals 1/2 gt squared. You have 10 meters equals 1/2 times 9.8 meters per second squared times t squared. And when you solve for t, you ended up with 1.43 seconds. And so the next step is to find that horizontal distance. So x equals x0 plus v0 xt plus 1/2 axt squared. The horizontal acceleration was 0. Let's make that initial position 0. And so you get x equals the initial horizontal speed, which is 9.9 meters per second, multiplied by the time we just found, which was 1.43 seconds. And that gave us a horizontal displacement of 14.1 meters. Okay, and that's it for example number 10.